So talking about logistic growth, it comes from a differential equation that looks like, usually we use dp dt is equal to k times p, and then times m minus p. And it's important for us to recognize what all of these different variables are in here. So m is just going to be some constant. M always represents our carrying capacity. So the amount that our differential equation, that our population is going to reach, or not quite reach, but the maximum value of our population. And we could talk about that. Basically, a logistic growth equation looks like this, right? It reaches some horizontal asymptote. That horizontal asymptote is that m value, that's the carrying capacity. This point in here in the middle where we have our point of inflection, this is always 1/2 of m, and this is when the population is increasing most rapidly. So that's another good thing to know. And obviously, the way that we solve the logistic growth differential equation is you just separate the variables. You bring the p times the m minus p down here, multiply by the dt, and integrate both sides. You have to use partial fraction decomposition to integrate that side. But the good thing to know is that this logistic growth differential equation, and you want to know this, and it's on the sheet also. I believe if it's not on the sheet, then you got to let me know. But the logistic growth equation is always solved into population equals carrying capacity divided by 1 plus m minus the initial population divided by the initial population times e to the negative m k t. So this is 100% of the time the solution to a logistic differential equation, always. Always. Good? That's something you should definitely know. And then, let's see, what else should we talk about this? Sometimes they like to ask a question about limits relating to these. So sometimes they'll ask, what's the limit as t approaches infinity of dp dt? And that should always be 0. And sometimes they'll ask, what's the limit as t approaches infinity of just the function itself, p? P of t is probably better. And that limit should always equal whatever your carrying capacity is. So these are two common questions that they like to sometimes throw in if they give you a logistic growth equation in the free response, or sometimes in the multiple choice. So they're asking, what is the limit of the rate of change of the population as t goes towards infinity? And since we're doing something like this, if it goes from exponential to then flattening off to this horizontal asymptote, the rate of change effectively becomes 0 as t goes towards infinity, because we're not we're barely increasing. And then the limit as t approaches infinity of the actual population function always ends up being your carrying capacity. Yeah, that's about it for logistic growth, I feel like. Is that, anybody have any questions on logistic growth stuff? Yeah, no problem, Nick. Everyone's good there. Okay. And just a quick reminder, you should know this too, but if you end up with dy dt equals k times y, we should know that this ends up being y equals y naught e to the kt, right? And this is just our regular exponential growth or decay equation. K is positive value, it's exponential growth. If k is a negative value, it's exponential decay. So just another one you should also just know that this differential equation is solved this way. That's not logistic growth, that's exponential, but good to know. All right. Anything else before we move into all the series stuff that we're going to review? All right. So first thing we'll talk about is let's start with just what's a geometric series. Seems like a good place to start since that's kind of where we started the unit with series. So a geometric series is just any series that each successive term is multiplied by some common ratio value. So something like 2 plus 4 plus 8 plus 16 and so on, where I'm just multiplying the previous value by 2 in this case. Right? And our generic form of it looks like some term plus that next term times the common ratio plus that next term times the previous term times the common ratio again of r, and so on, right? A plus AR squared plus AR cubed plus AR to the fourth plus AR to the fifth, and so on. I'm not going to go through how you go about determining what this series sums to and when it actually does have a finite sum. I mean, we're going to talk about it, but we're not going to prove it again, prove it in this year. If the absolute value of r is less than 1, or r is between -1 and 1, the geometric series will converge. And it should converge to a over 1 minus r. So your first term divided by 1 minus your common ratio. If r equals 1, or r is greater than 1, or less than -1, then the series will diverge. So easy to tell, and easy to tell if a geometric series converges or diverges. Just look for that common ratio. They don't always put geometric series on the AP test, but sometimes the series that they will give you in the free response will be geometric. And just look out for that, because usually if they give you one that's geometric, they will ask you what it actually sums to be, or if it diverges. And so if you can recognize that it's geometric, it should be really easy to do that. Sound good so far? Okay. So then what we did was, the next thing that we did, if I remember correctly here when we're talking about series, is we said, well, let's take a look then at this series of 1 plus x squared plus x cubed and so on, which is just a geometric series with the common ratio being x. And so we said that this series, which can be written out as the sum from n equals 0 to infinity of x to the n, just a geometric series with x as the common ratio, should then represent the function a over 1 minus r, first term over 1 minus x. And so this was the first series that we really started talking about in terms of algebraic stuff. It's called power series, and all of our other power series can pretty much be developed from this. We said that this power series was centered around 0, because all of these terms are just x terms, but we could have done something like x minus 1, x minus 1 squared, x minus 1 cubed, and then it would be a series centered around the value of x equals 1, or say a equals 1 usually. Let's see. What else do we do? We did stuff where we can take the derivative of any power series. So if I were to take the derivative of 1 over 1 minus x and the derivative of this, we could say that that would give us some other new series that would work out just perfectly also. So this would be the sum from n equals, and remember, if we took the derivative and we started at an n, we have to drop down to n equals 1, because this becomes nx to the n minus 1. And if I'm starting at 0, this first term then becomes power of -1, which is not what happens when you take derivatives of constants. That's why we have to raise our index up from n equals 0 to n equals 1. And we could say that that's equal to the derivative of this, which should be what? 1 over 1 minus x squared. And so we should be able to determine sometimes different series for other functions just coming straight from our regular functions from power series that we've already dealt with. You can also do the same thing with integration. So if we integrated this particular series, we'd see that it would just get us right back to this. We'd come right back to 1 over 1 minus x, and we'd come right back to x to the n. But we also can use this for things like, I think the one that we did in class was we said, let's try to find the series for the natural log of 1 plus x. And we said, well, we could start with 1 over 1 plus x. And the integral of that ought to be natural log of 1 plus x. And so what we did was we said, well, this series, this is equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the n. All we did was replace the minus x here with the positive x, so we have to flip the sign. And then we would just integrate this series, and that should give us natural log of 1 plus x. And so we say let's integrate that, and we write it in terms of like t or some other variable. But if we do the integral from 0 to x of 1 over 1 plus t, that should, if we integrate this series here, we end up with negative 1 to the n, x to the n plus 1 over n plus 1. I should have written my summation in here. N equals 0 to infinity of this, and that should equal the natural log of 1 plus x. And so we can use differentiation and integration to manipulate known power series to come up with series for new values. And eventually we started talking about the intervals of convergence. We talked back here about the interval of convergence for this. This is the absolute value of x is less than 1. So our interval of convergence was 1 to negative 1. And when you take the derivative of it, the interval of convergence stays the same. So derivative, we'll say interval of convergence does not change. Same thing with integration. The interval of convergence does not change, except maybe at, my handwriting is really bad. The endpoints. So whenever you integrate, you've got to go in and you've got to check and see whether the series represented by, in this case, plugging in 0 and, plugging in 1 and plugging in negative 1 into this, since the interval of convergence on this should stay as negative 1 to 1. If you plug in negative 1, is it true? And if you plug in 1, does it work out? Is it true? And so like for one, like natural log of 1 plus x, you'd find that you can't plug in negative 1 because that gives you natural log of 0, which doesn't work. So yeah, open bracket on negative 1, but if you plug in 1, we found that it did work. And eventually we later on were able to prove all of those endpoint convergence things by using a bunch of other, all those other tests that we came up with. Let's see. So far, so good. Or no? Any questions so far? All right. And then we developed a bunch of different series that we were supposed to know. And I've got them all written out in that test reminder. So I'm just, give me 1 second. I just opened that up so that I could just throw it into the document we were working on here. So the important power series that you want to know are these ones, along with the intervals of convergence for them. And so these are ones that you really definitely want to know the series representation of each one. Cool, we lost our toolbar here. That's fun. Means I can't go back to the pen. There it is. All right, are we all doing okay so far? All right, cool. Let's see here. What should we talk about next with these? Let's go with writing out a Taylor polynomial. So we came up with a method that allowed us to construct a polynomial of any degree. That should be a good approximation, a good representation of basically any function that we want, as long as we're able to take its derivative, which we should be able to do with pretty much any function. So we said that the Taylor polynomial or Taylor series that we could write should come from f of, we're going to center it at 0, f of 0 plus f prime of 0 times x, and we'll say it to the first, and we'll put this with our 0 factorial or 1 factorial, and then f double prime of 0 x to the second over 2 factorial, and f triple prime of 0 x to the third over 3 factorial, and so on. So as long as we know the function and we know how to take its derivatives, we can evaluate them at whatever value we want, we should be able to write out a series that should represent our function. And we can truncate it at any value that we want using this thing called the Taylor. We can do it centered on any value. So if I didn't want to center it at x equals 0, that's not 0. If I didn't want to center it at x equals 0, suppose I wanted to center it at like x equals 2. Well, then we do f2 over 0 factorial plus f prime of 2 times x minus 2 to the first over 1 factorial plus f double prime of 2 times x minus 2 squared over 2 factorial, f triple prime of 2 times x minus 2 to the third over 3 factorial, and so on. And when we truncate these, if we decide that we want to go in and truncate one of our Taylor series into a Taylor polynomial to approximate the value of the function, we just call it a second degree Taylor polynomial if we truncate it right here, whatever this power is up there. If I want it to be third degree, we truncate right here. If I just want first degree, we truncate it after those first two terms. Good or no? Everybody good so far there? All right. And let's see, specifically, if we do it at 0, I should probably put my arrow here. At 0, we call these Maclaurin series. If you're creating this series at 0, it's called Maclaurin series. So if you just see the term Maclaurin series, you know that you're talking about the Taylor series that's been centered. So sometimes they don't specify, they just use the term Maclaurin series. Maclaurin, the great Scottish mathematician who is buried in a cemetery in Edinburgh, which I have visited. Maybe someday you too can go see the grave of Maclaurin. Exciting times. Let's see, what else should we do? We could do, do we need to do an example of those, or do we feel pretty good about that? Making the polynomial. It is cool, isn't it, Nick? Maybe I probably took a picture of his grave. Probably. So if I did, I'll have to find it and save it into today's notes or something. Another thing to note is that we can manipulate any of these series. Like if I have, let's suppose I had, let's see, we'll go back here. Suppose I had the series, let's say for e to the x, but I wanted to find the series for e to the 5x. Well, we could just make this the sum from n equals 0 to infinity of 5x to the n over n factorial, right? And it should still converge for all real values of x, right? So we take whatever we had, if we had a 5x here instead of an x here, if it converged for all real x, and now it converges for all real 5x, which is all real x. Suppose we had something like natural log of 1 plus x, and we wanted to turn it into natural log of 1 plus 2x. We just replace the x with a 2x, and replace the 2x over here, or the x with the 2x over here, and we can just resolve the new inequality to find the new interval of convergence for that. And if I wanted to find the inverse tangent of x squared, I just replace the x with x squared, replace this x with x squared, and resolve to find the new interval of convergence. Easy enough or no? That's an important thing. All right, I believe the next thing we talked about was like errors due to truncation. And so I believe I've got these all in that sheet that I posted for you, but talk about the geometric series error bound should be probably the second easiest. If you truncate a geometric series, the error should always be equal. So let's say, well, I'll just write it out. The error is always equal to the first term after truncation divided by, well, not divided by, times your original series times, so times the series. So suppose I had, we'll just say, suppose I had our basic series 1 plus, for 1 over 1 minus x, 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th, and so on. And let's suppose I truncated it into a 4th degree polynomial. So we truncated it right here. Here's our truncation. Maybe truncate right here. Then that would tell us that the error that we might get from trying to evaluate, suppose we were evaluating, 1 plus a half squared plus a half to the 3rd plus a half to the 4th plus a half to the 5th plus half to the 6th forever, but we didn't know the actual value. If we truncate it here, we know that our error will always be no less than this next term, x to the 5th times the original series, which was 1 over 1 minus x. And so if we were trying to evaluate this at a half, we'd just do a half to the 5th divided by 1 minus a half. And we would know that the maximum error for this geometric series that we truncated after our 4th degree would be whatever that is. Looks like that's, I don't know. What is that? 164. Good on the geometric series error bound. It's always the next term after the truncation times the original series. Yeah, so suppose I was looking for, which we know that this converges for a half. Let's suppose I was looking for the sum from n equals 0 to infinity of 1/2 to the n. And I said, let's truncate it though after 4 terms. So my actual value would be 1 plus a half plus a 4th plus an 8th plus a 16th. And I would know that my error is always less than, error is always less than 1/2 to the 5th, so that next term divided by this 1 minus x, or times the original series, which was 1 over 1 minus x. So this would be 1/2 to the 5th power divided by 1/2. So whatever that comes out to be. But our error would always be less than that next term times the original series. That makes sense? Everybody good there? All right. The next error bound that we had was on alternating series. This was the easiest error bound. So the alternating series error bound, and we know that a series is an alternating series whenever it's got that sum from n equals 0 to infinity of a -1 to the n. Or if I got -1 to the n, or -1 to the n plus 1, or -1 to the n minus 1, as long as the coefficient on that n is an odd number. So if I had a 2n up there, it's not an alternating series, right? Because now I'm always raising -1 to an even power, which gives me all positive values. But -1 to the n makes this thing alternating. So we said that the alternating series error bound can only take place if three criteria are met. One is that the terms alternate, right? So we have to have three criteria. One, terms alternate. Two, that the terms decrease in absolute value. And three, that the terms approach 0. So if all three of those things are met, we can use the alternating series error bound, which just says that the error after, we'll say after, use a specific number, the error after n terms is the absolute value of the n plus first term. Right, so it's just the absolute value of the next term is the most that you might differ by if you have a alternating series. Everybody good with that? That one was, I think, pretty straightforward. We could give a quick example of that. So if we had something like, the series sum from n equals 0 to infinity of -1 to the n, x to the n, or effectively that's function 1 over 1 plus x is r is equal to -x, right? So the series looks like 1 minus x plus x squared minus x cubed plus x to the 4th, and so on. And let's suppose we were trying to approximate that at x equals 1/2, and we truncated it after 3 terms. We'd say that our value was this, but the error, we know that the error is always less than, now it's just, since this is an alternating series, that next term 1/2 to the 4th. And we always would put that in absolute value, even though we happen to have a positive value there. Want to make sure that put it in absolute value, because the error is never written as a negative value. And if you have a negative in front of it, then you'd show up with a negative answer and they'd take points off for that. Good or no? Right, and then for the one that nobody really likes, which is the Lagrange error bound. So the Lagrange error bound says that if you take any Taylor series and truncate it into whatever Taylor polynomial that you want to, you're always going to get some remainder. And basically, it's going to tell us that that remainder that we have is always less than or equal to the next derivative. I should guess an absolute value. The next derivative that we would have used for creating that Taylor series or that Taylor polynomial, evaluated at some value of c, where c is between x and a, between the x value we're evaluating at and the a value that we're centered around, times x minus a to the n plus 1 over n plus 1 factorial. So our remainder is always less than or equal to that value. I should make a note here that this c is on the interval from x, closed interval. It's on the interval from x to a or a to x, whichever way whichever one is smaller. Doesn't really matter. So C is on the interval from x to a and is the value that makes that n plus first derivative the largest. So our remainder there is always the n plus first derivative at the largest value C between x and a times x minus a to the n plus 1 over n plus 1 factorial. Good with that or no? All right. Let's see here. So we did the truncation, we did the error. What else? What else? I think if there's anything else before we did all these, just like all those other tests for convergence.
Batch, can you do like one example problem of something that we might be asked about the Lagrange error bound?
Sure. Let's see, what can I come up with here? Let's suppose, let's take a, I don't know, let's take a function like natural log. Let's do the natural log of 1 plus x1. That's pretty straightforward. Let's say we're looking for the natural log of 1 plus, we're using the function natural log of 1 plus x, and we want to, let's say we want to find the natural log of 1.2. And we are trying to find the bound on the error using Lagrange error bound. Supposing, let's say, let's truncate after, I don't know, let's truncate after 3 terms. So they said, what's the error using the Lagrange error bound if you truncate the series for natural log of 1 plus x used to evaluate natural log of 1.2 after 3 terms? So first thing we need to do is we need to write out, think about what that series looks like. So if you don't remember it, right, should remember it. But here it is. This is our -1 to the n minus 1 x to the n over n. So that should look like x minus x squared over 2 plus x cubed over 3 is our truncation. We'll go in, we'll write out some more terms. They just keep looking like this, right? But we're going to truncate right here. And so first thing we'd say is that it should be, our value here should be f triple prime of c for some c on the interval from between 1.2, or sorry, between 0.2 and 1, 0.2 and 0. Sorry, this is centered at 0. So we're looking at the interval between 0 and 0.2. So f triple prime of c times our x minus our a, which should be 0.2, right? X is 0.2 and a is 0. That should be 0.2. And sorry, not screwed that up. This should not be a third derivative because we've truncated after 3 terms. This should be the 4th derivative. So 4th derivative, this is 0.2 to the 4th, and then it should be over our, wow, that looks horrible. Where's my eraser? Sorry, I'm trying to get my toolbar back. It seems to have disappeared again. Come on, toolbar. All right, never mind. Can't get my toolbar. All right, we want the 4th derivative here at some value of c. times our x, and I guess I'll write it, x is 0.2 minus our 0 to the 4th over our n plus 1 factorial, so over our 4 factorial. And so this is what we're looking for. We need to find what value of c makes the 4th derivative of natural log of 1 plus x the largest possible value of it. So we have to find some quick derivatives here. If f is ln 1 plus x, f prime ought to be 1 over 1 plus x. F double prime ought to be negative 1 over 1 plus x squared. F triple prime ought to be, let's see here, that'll become, flip that negative, that becomes 2 over 1 plus x to the 3rd. And then the 4th derivative of that should become negative, what does it become? Negative 6 over 1 plus x to the 4th. And so we want to think about what makes this value the largest within there. So the number that I could plug in for x that is between 0 and 0.2 that makes this thing the largest would be plugging in 0 for x, because that's going to make my denominator the smallest, and the smaller my denominator is, the larger this value is going to be. So we're going to use x equals 0. That's the largest. F's 4th derivative will be on the interval from 0 to 0.2. Keep putting open intervals, but it should be closed, 0 to 0.2. And so we plug in 0, we end up with negative 6 is the 4th derivative of f at c. So we have negative 6, and remember, we're going to do this all in an absolute value. Negative 6 times 0.2 to the 4th over our 4 factorial. And whatever that comes out to be should be our answer. Let's see. The 6 will cancel with the 3 and the 2 of this, so we're just left with a 4 down here. This is 1/5 to the 4th, so what's that? 625 times 4, which ought to be 1 over 2,500. I think I did that arithmetic correctly. Does that make sense? So you just look for what value after your truncation makes that derivative the largest. Plug in your x minus your a that you're centered around to the 4th power over your 4 factorial, and that's your bound on the other. Good or no? Is that helpful? Not helpful? Does that make sense or no? Lots of you asked for. Yeah, Nick. Yeah, it shows 0 because it's on the interval 0 to 0.2. So let me go to another page here. My derivative became this, right? Negative 6 over 1 plus x to the 4th. My interval that I was looking at was 0 to 0.2, right? Because that's my a value that I'm centered around is 0. My x value that I'm plugging into this series is 0.2, because we're trying to find the natural log of 1.2. And so I have to pick a value on this interval for x that makes this the largest. So this is largest at x equals 0, because anything greater than that's going to make this a larger number down here. And when I raise that larger number to the 4th power, it's going to get even larger. Not that it's going to get big, but it's going to be bigger. And 6 divided by something that's bigger than 1 is going to be a value that is less than 6. And so I want that to be the largest it could possibly be. That's the largest it could possibly be when the denominator is the smallest it could possibly be. And the smallest on this interval that the denominator can be is when x is 0. Does that make sense or no? Cool. Everybody else, I know Darius and Aiden, you were both like asking about an example on that. So you guys good there? Everybody good with that? All right, cool. Okay. Anything else before we go into all of the assorted tests that we have talked about? All right. So I think the first test, if I remember correctly, the first sort of like extra test that we added in here was we just talked briefly about the integral test. And so we'll just touch on that for a second. The integral test is not one you probably have to use a ton, but it is the test that is used to prove the p-series test. So the integral test just says that if you have a function f, well, let's see. Okay, suppose we have a series a sub n that is positive Delphine, you're not gonna, I don't think you're gonna need to use the remainder bounding theorem, but just use the remainder bounding theorem to prove the convergence on like some of those functions like e to the x or sine of x to prove that they converge for all real numbers. You can use it to prove the interval of convergence, but you got a lot of other easier ways to do it. And I've never seen them specifically ask you to use the remainder bounding theorem to prove it. So best to just use one of the other simpler ways. Yeah. All right. So we have the sum of a sub n is our series here. We got positive terms for this, and if we can relate that series to a function, we'll call it f of. I don't know. We'll just call it f of x. That's fine. To some function f of x that is always positive and decreasing and continuous. That's important too. And continuous. Then we know that either both, and normally what we do is we'll use like some letter, we'll say n equals capital M to infinity of a sub n, and we'll say the integral from m to infinity of f of x. They both converge or both diverge. But they don't, one can't converge with the other one diverging. So if I had something in here like, we looked at a series of 1 over n, right? The series of 1 over n, which we know is the harmonic series and we know diverges. But if we look for the integral from, let's say, 1 to infinity of the series, of the function 1 over x, we get out that that is a divergent integral, and therefore the series itself also diverges. And this m value is just some index down here for which these things are always true for we'll say x greater than or equal to m. So that index, these things don't have to be true. I could have any values for this series. I could have any values for the series or for the function prior to capital M, some index, and then after m, this criteria is always met, and therefore both of the series will either diverge or both the series and the function will converge. And we used that result to look at p-series, and we knew that for any p-series, if we have the sum from n equals n equals 1 to infinity of 1 over n to the p, we know that this will diverge if p is less than or equal to 1, and we know that it will converge if p is greater than 1. And that's super important. You definitely want to know that. And you can just straight up use the p-series as a justification for why a series might converge or diverge. You can just say converges by the p-series test. If for some reason they ask you to prove this, the way you prove this is through the integral test, but I can't imagine that they will ask you to prove it. And we'll note that the special case of this, when p equals 1, is just the harmonic series. And you'll want to remember that the harmonic series diverges, but that the alternating harmonic series converges. So that's important. alternating harmonic series convergence. How are we doing? Good so far or no? All right. What other tests did we talk about? Let's see. We talked about the direct comparison test. So you can compare two series by direct comparison, so long as our series that we're looking at has no negative terms. So we need our series A sub n to be all positive. And you probably remember that that's a criteria that had to be met for pretty much every single test that we dealt with, that all the terms had to be positive. And we did come up with the way around that, right? If not all positive, what do we do? If they're not all positive, we just take the absolute value of it. And that tells us absolute convergence, right? Absolute convergence proves convergence. And so we proved that pretty easily a couple months back. So if we don't have all positive terms, just take the absolute value of your series and you can deal with it that way. So what the direct comparison test says is that the series A sub n will converge. So we'll say A sub n converges if for n greater than or equal to m, the A sub n is less than or equal to some other series, we'll call it B sub n, and B sub n converges. So if we know that some other series B sub n converges, and that at some index of m and beyond, all of the values of A are less than all of the values or equal to the values of B, then A must also converge. And likewise, that A will diverge if for, we'll use a different for n greater than or equal to capital N this time, A sub n is greater than or equal to, we'll call it C sub n, and we know that C sub n diverges. So if the one that we're always greater than diverges, then ours diverges. If the one that we're always less than converges, ours converges. For some index greater than, for some index that in there. The terms before this capital M or capital N value don't matter, because those are just a finite number of terms of a series, and those have a finite value to them. And then as long as you go towards infinity, this either this or this happens. Does that make sense or no? I think I gave an example, like, we have a series like 1 plus 7 plus 8, right, plus a half plus a 4 plus an 8 plus a 16. And if I just had the series of 1 plus, if I just had the series of, like 1 plus 3 plus 5 plus a half plus a 4 plus an 8 and so on, then we'd note that because this one, we know this one converges, we also know this one converges, even though after 3 terms, some of these values were larger than these values, because we know this one converges, and after the 3rd term, all of these are less than or equal to, they all happen to be equal to the terms of this series. This other one on top must also converge. Right, this is that m value that we're saying after that value of m, after an index of our index of 4 here, that takes place. Does that make sense or not? Everybody okay? An important one, easy one, forgot to talk about real quick, the nth term test for divergence. At the nth term test for divergence, this only, that's not only, I'm going to say this only guarantees divergence, not convergence. Very important that the nth term test for divergence only guarantees divergence. And it tells us if the limit as n approaches infinity of a series does not exist or does not equal 0, then this series diverges. Okay. So if you want to have a series that converges, the limit as n approaches infinity of the nth term of that series must approach 0. If it does not approach 0, then you are guaranteed that it diverges. But just because it does approach 0 does not necessarily guarantee that it converges, right? Because simple explanation would be 1 plus a half plus a third plus a fourth plus a fifth and so on, right? This is the sum from n equals 0, so n equals 1 to infinity of 1 over n. This is our harmonic series. This, the limit as n approaches infinity of 1 over n is definitely 0, but we know that this still diverges by p-series test. That's not a by the p-series test. Okay. So the nth term test does not indicate convergence, because if you tried to use it to indicate convergence, this would seem to show that it converges because it approaches 0, but that's not true. It does not guarantee that it converges. Everybody good with that on the nth term test for divergence? Because I've seen people on quizzes do that incorrectly and say that comes out to be convergent by the nth term test. That's never the case. Good? Not good? Good. All right. Let's see here. We talked about absolute convergence, implying convergence. The next test I think that we should briefly touch on is probably the most important of all of them, the ratio test. Right? The ratio test comes up all the time. The ratio test says, take a look for your series of a sub n at the limit as n approaches infinity of the n plus first term divided by the nth term, and get some value for your limit there. This converges if L is less than 1. This diverges if L is greater than 1. And it is inconclusive if L equals 1. You got to come up with some other test. This should be your go-to test anytime they say, does this series converge or diverge, or what's the interval of convergence, or what's the radius of convergence, or all of that. And if your series is has no x values in it, so it's not a power series, it's just some random series that they give you, you should just get a finite value for L, or you might get infinity, which will tell you that it diverges. But you should get some finite value for L if there are no x's in it. And then that'll just straight up tell you if it converges, diverges, or if it's inconclusive, and you got to find some other things to do. If you have a power series, if you have x's in it, you may end up with your limit equal to something like, x over 2, or who knows what it might be, right? So if your limit is x over 2, then you need to say, well, when is that less than 1? That's less than 1 if x is less than 2, greater than negative 2, something like that, right? And so you need to then, you need to make sure that you actually solve for the right values of x. So seen people in the past, they come out, they say, oh, my limit's got x's and I don't know what to do. Well, your limit has x's in it. That's still your limit. Set that inequality less than 1 and then solve it. Right? And remember, these are always, when we're doing this ratio test, we have to have positive terms. And so really what we're looking at is the absolute value of the n plus first term over the nth term. If they're all positive, you don't need the absolute value around it. But if they're not, you got to put it on there to determine the convergence. Good or no? That's probably the single most important test. I mean, you should remember all the tests, but if you only remember one test, remember this test. Another thing to think about is telescoping series. So remember, a telescoping series is one. I probably used this same example when we were doing the notes, but it's just an easy one, just to refresh our memories on it. If we have this series, and you try to do the ratio test on this, we're not going to go through it, but I guarantee you the ratio test is inconclusive on this one. So we don't know if this converges or diverges. But what we can do is we can use some partial fractions to separate this out. And 1 over n times n plus 1, if I remember correctly, this becomes, I hope this is right, 1 over n minus 1 over n plus 1. That's n plus 1, that's n minus. Yeah, that makes sense, right? Because if I get a common denominator, this becomes n plus 1 minus n, which just gives me the 1 up in the numerator over n times n plus 1. So this becomes this series, and if we look at the terms of this, the terms look like 1 minus a half plus, when I plug in 2, a half minus a third, when I plug in 3, a third minus a fourth, and so on. And we would note that this is why they call it a telescoping series, like those old school telescopes that collapse in on themselves. The negative a half and the positive half cancel, and the negative a third and the positive a third cancel, and the negative fourth and the positive a fourth cancel, and so on. And you are left with your final answer should just be this first piece of the first term, and then you need to, in this case, since it's a minus, now you need to subtract the limit as n approaches infinity of the second piece of this 1 over n plus 1, which just in this case happens to be 0, but it won't always be 0. And this comes out to be a value of 1. And so, well, we would be able to tell that this definitely converges because we found the value that it converges to. Good or no? The radius of convergence. What specifically about the radius of convergence are you asking about, Darius? So like the radius of convergence is, in this case, it's, let me just get a new page. Suppose we had down there a second ago, like, well, we'll just do it like this. If I have the absolute value of r is less than, how do I want to write this? This is what you do, right? The absolute value of x minus a is less than r. So this value of r, this is our radius of convergence. So if you can get as you're looking for the interval of convergence, if you can get your inequality down into this form, where it's the absolute value of a singular x, not 2x, not x over 2, but just x, and a coefficient of 1, plus or minus some number, is less than some other number over here. This r value is the radius of convergence. And the radius of convergence is always just half the entire interval. Right? It just tells us what half of the interval of convergence is. So from the value that we're centered around, so if I just had, if I just had absolute value of x is less than 2, my radius of convergence is 2. Since my a value is 0, I know that the interval on this should be -2 to 2. 0 is at the center, I go 2 units to both sides. If I had something like absolute value of x minus 1 is less than 3, then I would know that r is equal to 3. And I would need to center myself here at 1. So if I'm saying I'm at a equals 1, then that would put me at a 4 here, right? And then a -2 here, 3 units to the right of 1 and 3 units to the left of 1. Does that make sense? And this is the form you should get, out of the ratio test and out of a lot of the other tests that we haven't started dealing with yet, but that we will deal with, I guess, tomorrow, since we're pretty much out of time here. Could be used the nth root test or stuff like that. Does that help, Darius, or no? Cool.
Yes, it does. Thank you.
Perfect. Look at that. Another first period of math complete.